Welcome back. We were in the process of discussing the concepts of magnetism of grade 12. So, before the break we are talking about the movement of a charged particle in a magnetic field. Now, let us see what happens when the charged particle is entering a region where there are both the fields, like both the types of field, electric field and magnetic field. Such a region is what is normally called as the crossed region of the fields, crossed fields. Okay. So, that is just imagine if there is an electric field like this. See, this is an electric field. Now, the electric field is acting from where to where? From positive to negative. You say the electric field is directed like this. Imagine a charged particle enters with a velocity v in this electric field. So, what will happen over here? You can see it will always move towards the negative plate. So, which you can easily see with the help of a simulation. You just look at the watch the screen. Okay. So, now you can see one thing, a charged particle is entering a field. Okay. There is an electric field. See, you can see, I think all of you can see this. There is a red line and a blue line. Red line is indicating the positive side and blue indicates negative side. Charged particle is a positive charge and it is entering the field. You see what is happening. See, it is deviated towards the, you see the path, it is deviated towards the negative side. You know, the positive charge particle always attracts, it attracts towards negative side. Okay. So, once again I will show you, since if I am changing it to, see, the direction of electric field is changed. Okay. Now, I am using electric field the other way. Okay. Now, the down is positive, up is negative. Now, if you increase, if you let the charge particle go, so I am changing the, see, it will tend towards the negative side upwards. Okay. So, it follows a parabolic path, you can see. Since the particle is negative, it would be like this. Okay. Now, next thing is, again considering the electric field in this direction, you see, from positive to negative, okay, top to bottom, that is the direction of electric field. Okay. And charge particle, now I am changing the charge particle to negative particle. Okay. Now, it is a negative particle, you see what happens to the negative particle, what happens if the negative particle is moving. Okay. So, it is going so that, you know, it is tending towards positive side with a force. You know, this arrow mark, that is indicating the direction of the force experienced by the particle under the influence of the electric field. Okay. Now, what else is, I am going to keep the electric field 0. So, no electric field. Okay. No electric field. Okay. Electric field is not there, only magnetic field is there. Now, I am going to introduce a magnetic field along the Z axis. See what is happening. See, in a magnetic field, it will again, see, it is actually, it is a small region only. With this velocity, its tendency will be to go in a circular path. The direction of this force is the force by the magnetic field, that is what is leading to the centripetal force, which I showed you before. The other simulation I showed you, which shows the charged particle is moving only in the circular path. Okay, this is the case of magnetic field. Now, next aspect is, I am going to show you the situation when there is both, there are both the fields like electric field and magnetic field. First, I will show it to you on the board, then I will show it to you on the screen again. Okay, watch the board here now. Okay, so the charged particle entering a an electric field alone, according to this, we have seen it will tend to go like this. That means there is a force acting this way. Okay, so this is the force by the electric field. Write it as Fe. Force by the electric field. Okay. Now, the picture is, I am going to introduce a magnetic field as well. Okay. So, within the circle, you imagine there is a magnetic field. You know, the dots here represent magnetic field in the positive Z axis. So, there is a magnetic field acting towards the positive Z axis, that is outwards. Charged particle is entering this way. Now, imagine only magnetic field, there is no electric field. So, if there is only magnetic field, can you say what will be the direction of force by the field on the particle? Only magnetic field. So, in that case, again you use Fleming's left hand rule. I told you the charged particle positive means the same direction itself, we can assume the direction of current like this. And how about the magnetic field? It is outwards. So, it would be like this. Okay. So, the force is, the magnetic field is outwards, the current is down since the particle is positive, particle is coming down, but if it was electron, it would have been the other way. Okay, so now it's positive charge particle, it's coming down. Okay, this is the magnetic field. So you see what's the direction of thumb? Thumb is towards left. So you see that there is a force acting by the magnetic field towards left. So that is Fm. So now from this discussion, what we understand is there are two types of forces existing. One is due to electric field, the other one is due to magnetic field. Due to electric field, the forces like this towards right. Due to magnetic field, in this situation, forces towards left. Now what else you have to understand is, you know, how much is the force by the magnetic field, that surely depends on the velocity, how fast it is coming, it is a factor. So that means, suppose the group of charged particles coming over here, entering this region, they possess varying velocities. Maybe some will have high speed, some will have low speed. Okay, if varying velocities are there, slow moving particles will be experiencing only less force by the magnetic field. Slow moving particles. So there, which force will dominate? Force by the electric field will dominate. So what will happen? Such particle will have the tendency to go towards the force by the electric field, that is towards right it will go. Whereas fast moving particles, high energetic particles, high speed particles, when they are entering the region, speed more, force more. So the force experienced by the particle due to magnetic field will be the higher, right? So such particles will have the tendency to move towards the direction of force by the magnetic field. So it will go this way. So simply, slow moving particles will move in this diagram. Slow moving particles will go towards right and fast moving particles will go towards left. Now we think of those particles which possess a particular velocity such that the forces are equal. That is, whatever be the force experienced by the magnetic charged particle by the magnetic field would be the same as that by the electric field as well. These two forces are equal. And of course, you have seen in this diagram, the forces are equal and the forces are opposite as well. If the forces are equal, remember the velocity of the particle should be such that the forces should be the same. In this case, we will see that V is equal to E by B, that is all the charged particles coming out. So what will happen to such particle if the forces are equal? These particles will not go towards right or left, because forces are balanced. Such particles will come straight. Correct? So if you keep some some filter or some opening, a small opening over here, some filter is there, then what happens is those particles which are coming straight down from this arrangement, coming straight in whatever the initial direction, same direction itself of the charged particle is coming out, all these particles will have the same velocity, which is given by V is equal to E by B. Right? So this is the basic concept of velocity selector. So where do we use velocity selector that way? The velocity selector is, say for example, we have got a group of charged particles in which varying velocities are there. But in the varying velocities, one of the just think of maybe 5 meter per second, or we want to select those charged particles possessing velocity of 5 meter per second, let's say only 5 meter per second. So out of different velocities, only that 5 meter per second charged particles to be collected out. So what we will do is we will make an arrangement of this sort, okay, in which there is electric field and magnetic field, right? And what else is there? Adjust the strength of the electric and magnetic fields in such a way that E by B, strength of electric field by strength of the magnetic field, that ratio should be 5. Maybe if this is 50, this should be 10, right? If this is say 25, this should be 5. So the ratio should be 5 meter per second. Then all the charged particles coming out all will have 5 meter per second velocity. So we say therefore this arrangement, that is arrangement of crossed electric and magnetic fields, is used to select the velocity from a group of charged particles. So that's why this arrangement is what's called velocity selector or velocity filter. Okay, this I will show it to you on the screen again with the help of a simulation, after which you will do some numerical problems. You now have a look at the screen again. Okay, so now there is in this diagram or in this on the screen you can see there is an electric field acting downwards. Its value is what you can see here, minus 0.5, it is downwards, and no magnetic field. Okay, now I am going to apply a magnetic field. So along the positive Z axis I am going to apply a magnetic field. See, what you observe here is you can see one thing, the force by the charged particle entering is positive. Okay, it is, there is a force. You see this arrow, down arrow is representing the direction of force by the electric field, and the other arrow is representing the direction of force by the magnetic field. So which one is greater? The force by the magnetic field is greater. So that is why it is going towards that side. See, it will go towards that side. But now think of another situation, that is, if the charged particle is, if I am going to decrease the strength of the magnetic field, okay, the force by the, see, force by the magnetic field is decreasing, correct, but I am going to make another change in this setup, that is, initial velocity is 2, y component of electric field, x component of electric field I am keeping it as 2, and z component of electric field I am keeping it as let us say 4. Okay, so electric field is 2, electric field is 0.2. Let me take it another way. Electric field I am keeping it as 0.1, and magnetic field I am keeping it as 0.5. Okay, E is 0.1 and B is 0.5. All right. So then let us see what is happening here. Here both the forces act in the same direction, so it will be added up. How about if the particle is made negative? Okay. Now you see what is happening. If the particle is made negative, both the forces will be acting upwards. Okay. Now what else is? I am going to change it in such a way, again positive charge. The y component of the electric field we have here minus 0.5. Okay. So I am going to change it to say 0.6, and the other one is, see, now what you see is both the forces add up. Okay. Now if I reverse the direction, now you can make out one thing. You see, this is what exactly happening in velocity selector arrangement. These two values you will be able to, you can notice here. The velocity is, I kept the velocity as 2 meter per second, but you see the ratio of the electric field to magnetic field, 0.6 is electric field, 0.3 is magnetic field, 0.6 by 0.3, that is 6 by 3, 2. So what you observe here is the ratio of the electric field to magnetic field is simply same as the velocity of the charged particle itself, E by B is equal to V. Now that is what you observe here, the charged particle goes in a straight line, it is not at all deviated away. You can clearly see that the two forces, these are two vectors, these two forces, force by the electric field and force by the magnetic field, are equal and opposite. That is why they are cancelled off. That is why the velocity will be the same, which is the initial velocity itself, in the same direction. Okay. So this is the concept of velocity selector. I hope all of you understood the concept of velocity selector. That is nothing but, so what is a velocity selector? Velocity selector is an arrangement used to select the velocity of a group of charge from a group of charged particles. We want a specific velocity of the charged particle. Actually, in nuclear reactions and all, we will need some charged particles with a specific velocity. Okay. In such a situation, we will use this kind of arrangement. There is a in chemistry you might have studied, there is a setup called spectrograph, mass spectrograph. The particles are to be arranged in terms of their masses, for which initially they will be selected for a particular velocity. There we will use velocity selector arrangement or velocity filter arrangement. Okay. That is a concept. Now, as I promised at the beginning, we will now do a few numerical problems based on this chapter. Okay. So these are some of the questions randomly picked up. Yeah. Okay. So you can see one question. All of you go through the question carefully. So I will explain this over here on the board. So I will read it out for you. Find the magnitude of the force on each segment of the wire shown below. If the magnetic field of 0.3 Tesla is applied parallel to AB and D, take the value of current as 1 ampere. So just look at the picture itself. I will show it to you on the picture itself. I hope all of you can see that. Okay. Okay. You just watch this. So will you be able to see this? Okay. All right. So just look at the segment AB. So we have the segment AB and one segment BC, then CD and DE. okay, the current flowing is 1 ampere. Now I will explain this. The magnetic field is like this. Okay, now you look at the board. Okay. So the value of magnetic field is given as 0.3 Tesla. You know which concept you will make use of here. This is simply the equation we use for calculating the force on a on a current carrying conductor by the magnetic field, which is actually I mentioned at the next segment this comes, that is the equation is F is equal to BIL sin theta. F is equal to BIL sin theta, that is the equation for the force on a current carrying conductor when placed in a uniform magnetic field. So here you can see this is one segment AB, but you see this AB, this current 1 ampere is in fact parallel to the magnetic field. This is the direction of magnetic field. So parallel. So what will be the force here? Here the force is 0. Force on this segment is 0. How about here? Here also force is 0 because they are parallel. But look at this. This is like in fact perpendicular magnetic field. So in perpendicular, the conductor is perpendicular to the magnetic field. So the equation we have to use over here is to find the force BIL, because sin theta is 1. Right, B is 0.3, current is 1 ampere, length is given as how much? It is given as 8 centimeters, but remember centimeter you have to convert to meter, multiplied by 10 to the power minus 2. Okay. Now look at this conductor. So there is a force existing on the conductor CD as well. So what will be the force there? You will use the equation F is equal to BIL sin, you know what is the angle between these two, that is current and the conductor. Here the angle given is 60 degree. But we want the angle between the magnetic field and the conductor. So the magnetic field is this one, conductor is this. So the angle between them is nothing but 90 minus 60, right. So the angle is 30, sin 30. So the equation to use for calculating the force on CD is BIL sin 30. So all of you understood the question and answer. That is, in these two segments the force is 0, and this segment maximum force because the angle is 90 degree, and over here the force is BIL sin 30. Okay. So now you have a look at the next question. Just look at the next question. Okay. All of you read the go through the next question first. There is a magnet and there is a loop as well. Both are at a distance r. Center O. Okay. So the question is, this is given a small magnet of dipole moment M, capital M. Okay. It is placed in at a distance r from the origin. Okay. You can clearly see it from the diagram on the board also. Okay. There is a small coil placed on the x axis, okay, at the same distance from the origin. This is the origin. Question is, for what value of current in the coil does a magnetic needle kept at the origin remains undeflected? That means here there is a magnet that causes a magnetic field at this point. The question is, for what value of current in this loop the magnetic field at this point should be 0. Means otherwise it is given that a magnetic compass will remain undeflected. Undeflected means simply no magnetic field. How is that possible? We can say the magnetic field by the magnet gets cancelled by due to the coil. That is, if you look from this side, the direction of the current in the coil, first of all let us find out what is the direction of magnetic field at this point due to the magnet. You know the bar magnet causes magnetic field lines, or it has magnetic field lines from north to south like this. Okay, so at any point over here if you draw a tangent, the direction of magnetic field by the bar magnet is this way. So over here the magnetic field by the magnet is like this. Clearly you can see that the point O is at the on the perpendicular bisector or the equatorial line of the magnet, but it is given as a short bar magnet. So what is the value of Bm? Bm is mu 0 by 4 pi, right, mu naught by 4 pi. It is a perpendicular bisector. Okay, so m by r cubed. Why it is m by r cubed? Simply because it is a short bar magnet. Now that magnetic field should be cancelled by a magnetic field by the conductor with this loop. The current loop should produce a magnetic field in such a way that should be opposite and equal. So I will write it as Bi, the magnetic field to the current. Now, can you say what should be the direction of the current in this? If you look from this side, always one point remember, if the current is in the clockwise direction, the magnetic field is into the plane, and if it is in the anti-clockwise direction, it is out of the plane. So, you look from this side, there is a current in the clockwise direction, and if the current is clockwise direction, the magnetic field is like this, so there will be current magnetic field in this way. So, direction of current we found out. Now, only thing is that we have to equate this with the current due to the magnetic field due to the coil. So, coil's magnetic field, we have an equation mu naught I r squared. This r is this radius. Okay, its radius, you take it as r, yeah, divide by 2. The distance is quite large compared to the radius of the turn, because radius of the turn, it is like you take it as negligible when you add. So, that is why this equation can be reduced to r cubed. Okay, so, r cubed, it will cancel. So, we can solve and find value of I. So, calculate the value of I or obtain an expression for I from this expression, and write the direction of current as clockwise when viewed from right side. So, once again, what was the question? For magnetic field at this point to be 0, what should be the current in the loop? Okay, for magnetic field to be 0. So, for the current to be 0, for the magnetic field to be 0, the direction of current should be clockwise when you look from the right side, and you are equating the field due to the current and the field due to the short bar magnet. We are equating both, and you see that this is, since it is small, r cubed you can cancel and solve and find the value of I. Okay, that is one question. Now, look at the next question, all of you. So, have a look at the next question also. So, I think we have time to do one more question, a small question. Okay, have a look at the question. So, we have two magnets kept like this. Okay, their dipole moments are given m and m root 3 to form a cross. The combination suspended in a uniform magnetic field. The magnetic moment m now makes an angle theta with the field direction. Find the value of theta. Okay, so, in this question, you are given two dipoles. Okay, one dipole moment is like this m. Another dipole moment is perpendicular to that is m root 3, otherwise root 3 m. So, when you suspend a bar magnet, the basic concept you should have is, when you suspend a bar magnet in a magnetic field, always the magnetic field will align in the direction of the external. So, the dipole will align in the direction of the external magnetic field. If it aligns in the direction of external magnetic field, simply what does it mean? It means it is in equilibrium. Okay, I will explain once again. Here we have not simply a single dipole, there are two dipoles. So, there is a dipole moment m. This is the resultant. There is a dipole moment, resultant dipole moment. This resultant should be along the direction of the external magnetic field, then only it will be in equilibrium. Okay, then only it will be in equilibrium. So, the external magnetic field should be like this. So, here we have theta is given. So, what you will do is you just take tan theta here, tan theta is equal to root 3 m by m. So, it is root 3. So, theta we get as 60 degree. So, 60 degree is the answer. Today anyway we have it is the time for us to wind up today's session, today's class. Again, if at all you have got any confusions, please feel free to call us and get back to us in through our mail or any of these numbers given. So, anyway, I hope all of you could absorb something from the chapter magnetism. We will again meet the next session with another topic for grade 12. If at all any other classes, if anything else to be discussed, you can tell us as well. We will go for that as well. Okay. So, anyway, we will see again for today's class. We are finishing off for the time being. Stay tuned with NTV. See you again.